Go ahead.
So problem number 8 is a ball is dropped from rest at a height of 80 meters above the ground.
All right, so something's dropped from an 80-meter height. So it's gonna like speed up. I'm just doing a motion map. That's how I work. I try to figure out the motion first. So it's dropped. That means when you hear the word dropped, that means it was probably released from rest. Does that make sense? So it's like that then. In the beginning, when it was released, there was no velocity when it was first released. We also know its acceleration must be 9.8 meters per second squared downward, right? So the acceleration is just like this, and the acceleration never changed. You with me so far? Did you do the problems leading up to this? It would be important to do them in order, because this is a hard one. All right, so then maybe I draw a couple graphs, sketch a couple graphs, okay? Position, velocity, acceleration. All right, and then this is like meters per second squared, seconds, and then we got like, okay, we got which direction you have to choose for every problem. What direction you want to be positive? Up or down in this case?
The positive direction to be up.
Well, if you make up positive, do you notice that your accelerations are all down?
Yes.
And your velocities are all down? Then you can have negative accelerations, negative velocities. You really want that? It'll still work. It's just, why not make positive downward? Then everything's positive. Accelerations are positive, velocities positive. And so now I know my acceleration is going to be a positive 9.8, right? So that's 9.8. That's the acceleration. It's acceleration due to gravity. We'll just use 10. And then the beginning velocity is 0, and it's going to like speed up, and all the velocities are positive, right? And then the position time graph is going to be a curve with positive slopes, because the velocities are all positive. It's moving in a positive direction, and it's speeding up, so the slopes get steeper. So there's my graphs. Now, what do we know? We know 80 meters is how far it falls. So maybe I'll make this dotted vertical line, and I'll just say, okay, this object, this area here is my change in velocity. This area here is my change in position, because that's a velocity graphs area. So what I would do is I'd say, okay, well, I know 10 times t is my change in velocity. See, I figured that out. And then, because that's the area of my acceleration graph, so that means my velocity here is 10t, because I started with 0 velocity, and my change is 10t in velocity. So my I don't know t, but I know that area here has to be an 80 meter displacement, because I'm told it fell 80 meters, right? And then the 80 meters has to equal, I'm going to leave out the units because it's a little bit easier. So the 80 meters has to be equal to 1/2, that's the area of a triangle. Tell me the height. Times t is the height, right? And what's the base? Do we know time?
Just t.
Yeah, we don't know it, so we're going to call that t. So I can solve this equation. This equation came from the area of my velocity graph. And solving it's no big deal. Multiply both sides by 2. I'll get 160 equals 10t squared. Do you see I got that? And then I could divide both sides by 10. Don't I get like 16 here and t squared there? What's t going to be, home chicken? For what? Time has to be in seconds. Good. All right. And the way it works is this number, the units are meters per second squared. This number, the units are meters, right? So when I simplify this, I have meters here, right? Because 80 times 2 is still meters. And then I divided by 10 meters per second squared to get my 16. And the 16 became seconds squared when I did that. So when you divide your meters by your meters per second squared, it's kind of complicated, but that simplifies to give you 1 over 1 over seconds squared, which simplifies into just seconds squared, which is the units here. And then when I took the square root, it's simplified to seconds. And so I'm pretty sure it's correct because the units seem like they work out. And that's the time to fall 80 meters. You like it?
Yes.
And then what was the other question here? How
long does it take?
Oh, so I did B first, and then the other question is how fast is it going? So I did B, and then now I'm going to do A. I didn't do them in order. Oh well. So I would find the time first. You notice we have this here? So I can find the change in velocity, right? What's my change in velocity going to be? 10 times t. Well, I just found t, right? What's t? Okay, so 10 refers to meters per second squared acceleration, right? Times 4 seconds. And that will give me my change in velocity. And since my object started with 0 velocity, what that means is the change in velocity, if you start from 0 and then you change by, what is it, 40? This is 40 meters per second because this seconds and that cancels. So I changed velocity by 40 meters per second. I started at 0, so my velocity just before I hit the ground must be 40 meters per second. So it looks like I found the speed after falling 80 meters. And as long as we ignore air, which I'm doing here, it wouldn't even matter what object we dropped. If it fell 80 meters, this is how fast it's going. And that's the time it takes.
Okay.
All right? Ignoring air. And we'd also have to make sure that we're near Earth's surface. That's important too. Do you think this would work out on the International Space Station? It'd work out okay because that's only 10 miles up from the Earth's surface. And the distance from the space station to the center of the Earth and the distance from where we live on the Earth's surface to the center of the Earth, it's still about the same distance. So the astronauts, even though you see pictures of them floating, they're still following this same acceleration due to gravity. They're actually falling, which is kind of cool to think about. Anyway, hope that helped.
Yeah.
And I'll put this up for everybody.